Hi. Fibonacci numbers and Lucas numbers have a lot in common. So for both of these sequences, every number is sum of the previous two numbers. So for example, 1 is equal to 1 plus 0. 2 is equal to the previous two numbers are 1 and 1. 1 plus 1 is equal to 2. And 3 is equal to 2 plus 1. 5 is equal to 3 plus 2, and so on. So same pattern happens for Lucas numbers as well. So 3 is equal to 2 plus 1. 4 is equal to 3 plus 1. Previous two numbers are 3 and 1. And 7 is equal to 4 plus 3, and so on. That is the first similarity between Fibonacci numbers and Lucas numbers. Secondly, Fibonacci numbers and Lucas numbers both exist in nature. For example, let's take a look at these flowers and count how many petals they have. So this one, 1, 2, 3, 4, 5 petals. This flower, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 petals. And this flower, 1, 2, 3. 3 petals. So 5, 13, and 3. These numbers, 5, 13, 3, are all Fibonacci numbers. Human body, for example, we have 5 fingers, and each finger has 3 parts. So 3 and 5 consecutive Fibonacci numbers exist on human body as well. But I believe there are different combinations of Fibonacci numbers exist in nature. So let's take a look at one example. So these are Fibonacci numbers: 0, 1, 1, 2, 3, 5, 8, 13. The next number would be 21. 21 plus 13, 34. So now, if we take every 2 consecutive Fibonacci numbers and make a linear sequence, what's a linear sequence? For a sequence to be linear, the differences between the consecutive terms must be the same. For example, 2, 4, 6, 8, 10. So the difference is always 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. And 8 plus 2 is 10. So this is a linear sequence. Or 1, 2, 3, 4, 5. The difference is always 1. 1 plus 1, 2. 2 plus 1, 3. 3 plus 1, 4. That is also a linear sequence. What if we take every 2 Fibonacci numbers and then make a linear sequence? For example, 0 and 1, the first 2 Fibonacci numbers, 0 and 1. The difference between 0 and 1 is 1. 0 plus 1 is 1. If we make a linear sequence, we just add 1 because the differences must be the same. 1 plus 1 is 2. Now we will keep this number, 2. Now let's take this second consecutive Fibonacci numbers, 1 and 1, right here. The difference between 1 and 1 is 0. Since the difference must be same for a linear sequence, I'm going to add 0 again. 1 plus 0 is 1. So now we will keep this 1. It's already in bold color. So next 2 Fibonacci numbers are 1 and 2. Difference between 1 and 2 is 1. So 1 plus 1 is 2. Now we add 1. 2 plus 1 would be 3. So the next number is 3. And we take 2 and 3. The difference between 2 and 3 is 1. 2 plus 1 is 3. So 3 plus 1 is 4. So the next term would be 4 if we make a linear sequence. So these sequences became all linear. And 3 and 5, the difference between 3 and 5 is 2. 3 plus 2 is 5, and 5 plus 2 is 7. So now, if we look at these numbers in bold color, 2, 1, 3, 4, and 7. These numbers are Lucas numbers. So we used Fibonacci numbers and created Lucas numbers just by taking every 2 consecutive Fibonacci numbers and making a linear sequence each time. So that is another relationship between Lucas numbers. The Lucas numbers are 2, 1, 3, 4, 7. Next one would be 11, 18. And the Fibonacci numbers 0, 1, 1, 2, 3, 5, 8, and 13. But there's an easier way to find the next term, which is using the numbers in Pascal's triangle. Pascal's triangle is this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 4. So 1, 4, 6, 4, 1. So this is called Pascal's triangle. If we take these numbers 1, 2, and 1 and use these numbers as coefficients and multiply these numbers by the Fibonacci numbers, we still can get these Lucas numbers. So how? So right here. So Fibonacci numbers are 0, 1, 1, 2, 3, 5, 8. So I take the first 2 Fibonacci numbers, 0 and 1, right here, 0 and 1, and I multiply them by the coefficients 1, 2, and 1. As we see, 2, 1, and the last one is times 1, but multiplying by 1 is not necessary. That's why I didn't put times 1 here. But I have used 1 to 1 from the Pascal's triangle, which is 1, 1, 1, 1, 2, 1. So we can use 1 to 1 to find the next term. So we take 1 and 0 and create the 2. Now the next 2 Fibonacci numbers are 1 and 1. So I'm going to use 1 and 1, multiply them by the coefficients 1 and 2, then we get 1. So 2 times 1, and then minus 1 times 1. Each time we multiply by 2 and 1. Next, we can take 1 and 2 and multiply 2 by 2 and multiply 1 by 1, then subtract. 2 times 2 is 4, 1 times 1 is 1, 4 minus 1 is 3. Next, we take 2 and 3 to multiply 2 by 3 and then multiply 1 by 2. Then we subtract. 6 minus 2 would be 4. So the next one would be, if we use 3 and 5, we multiply 2 by 5. 2 times 5 minus, then multiply 1 by 3. 1 times 3. 2 times 5 is 10. 10 minus 3 would be 7. Okay, then I will do one more. 2 times, now, but this time I will use 5 and 8 right here. So 2 times 8 minus 1 times 5. 2 times 8, 16. 16 minus 5 would be 11. Now let's rewrite these numbers, the resulting numbers. The resulting numbers are 2, 1, 3, 4, 7, 11. So these numbers are Lucas numbers. But Lucas numbers are already known. So I believe there are we can make different combinations, and the different combinations of Fibonacci also exists in nature. So next page, right here. This I still use the Fibonacci numbers. Fibonacci numbers are 0, 1, 1, 2, 3, 5, 8. And this time I will use the coefficients 1, 3, 3, 1. So we see 1, 3, 3. We don't see 1, but the last one is right here, times 1. So we take the first three Fibonacci numbers, 0, 1, 1, and multiply them by the coefficients 3, 3, and 1, and we find the next term. So right here, 0, 1, 1. What would be the next term so that it's going to be quadratic? So in the previous sequence, it was linear, but this time, let's make it quadratic. To make it quadratic, the second differences must be the same. The difference between 0 and 1 is 1. Difference between 1 and 1 is 0. A difference between 1 and 0 is 1. Since the second differences must be same, then so the second differences must be same. 1, 1, 1. So what would be the next term? We add 0 and 1. 0 plus 1 would be 1. And we add 1 and 1. 1 plus 1 would be 2. 0, 1, 1. 2. So 3 times 1 minus 3 times 1, and then plus 1 times 0 equals 0. And this time we take 1, 1, and 2 and multiply these numbers by. So 3 times 2 minus 3 times 1, and then 1 times 1. And the order is minus, plus, minus, plus. So when we look at the resulting numbers, 0, 4, 4, 8, 12. All of these numbers are divisible by 4. So we divide every single resulting number by 4. 0 divided by 4 is 0. 4 divided by 4 is 1. 4 divided by 4 is 1. 8 divided by 4 is 2. And 12 divided by 3. So 0, 1, 1, 2, 3. Next number will be 5 Fibonacci numbers. But I believe these numbers, 0, 4, 4, 8, 12, these numbers, consecutive numbers, also exist in nature. That's a different combination of Fibonacci. And one more, actually 2 more. We can also use 1, 4, 6, 4, 1 from Pascal's triangle and take every 4 consecutive Fibonacci numbers, 1, 2, 3, 4. So we will take 0, 1, 1, 2 and multiply these numbers by 1, 4, 6, 4, 1 in order. Then subtract, add each time. So 4 times 2 minus 6 times 1 plus 4 times 1 minus 1 times 0. That is equal to 6. If we keep doing this, we are going to get 6, 3, 9, 12, 21. That's another sequence that I made. These numbers are all divisible by 3. So 6 divided by 3 is 2. 3 divided by 3 is 1. 9 divided by 3 is 3. 12 divided by 3 is 4. And 21 divided by 3 is 7. So 2, 1, 3, 4, 7. These are Lucas numbers. So when we apply when we use the coefficients 1, 4, 6, 4, 1, we get a different combination of Lucas numbers this time. So what if we use 1, 5, 10, 10, 5, 1. All right, right here. But this sequence is my favorite. 0, 11, 11, 22, 33. I have created this sequence by using the coefficients 1, 5, 10, 10, 5, 1. That is also from Pascal's triangle. This time, we take every 5 consecutive terms of Fibonacci numbers. So 1, 2, 3, 4, 5. So I'm taking these numbers 0, 1, 1, 2, 3. 1, 2, 3, 4, 5. Yes. And then multiply these numbers by 5, 10, 10, 5, 1. And then the resulting number, the first one would be 0. Then I take 1, 1, 2, 3, 5 and multiply these numbers by 1, 5, 10, 10, 5, 1 in order, and I get 11. Then I take 1, 2, 3, 5, 8, the next 5 Fibonacci numbers, and then multiply these numbers by the coefficients 1, 5, 10, 10, 5, 1, and I get 11 again. So when you look at these resulting numbers, 0, 11, 11, 22, 33. All of these numbers are divisible by 11. 0 divided by 11 is 0. 11 divided by 11 is 1. 11 divided by 11 is 1. 22 divided by 11 is 2. And 33 divided by 11 is 3. So 0, 1, 1, 2, 3. Fibonacci numbers. So I believe different combinations of Fibonacci numbers also exist in nature. Thank you for watching.